Hi, everybody. Welcome back. We're continuing on here today with analog and digital audio. This lecture is building off our previous lecture on sound and thinking about frequency and hertz and thinking about amplitude and decibels. Building off that conversation, make sure to watch that video before you watch this one. And we're going to be talking about both recording and the history of recording and sort of the more specifics of digital recording, which is how we engage with recording when we use computers or other digital technology. So in the world of audio signals, a significant divide exists between analog and digital, right? We'll often hear these terms. What do they mean, right? An analog signal is continuous and reflects a physical change. Think of watching a speaker move as it pumping a bass frequency. So if you've ever looked at a studio monitor speaker, another speaker, actually the cone moving, right? We can see that that is causing that disturbance in the air, right? So speakers receive an analog signal. A digital signal presents data as a sequence of discrete separated points that sample the original audio. So we're looking at digital audio. We can think about it sort of like a film. When we have a film, we have a bunch of still photographs that we play together in quick succession. So it's a little bit different than an analog signal where there's no stopping. There's just continuous movement, right? We'll dive a little bit deeper into what the differences are between these and sort of the technologies used to create analog and digital recordings. So first, let's start with analog recording because this represents the sort of history of recording. So what does analog mean? It's important to think about with this word, the history of this word, right? This comes from Greek and it means the same, something that is the same, right? So analog, you could think of it, the word analogy, right? An analogy is sort of we're comparing two things, right? So in a way, the sound that I'm producing with my voice right now, if I was to use a tape recorder, that analog recording is the same, right? The continuous disturbances of air caused by my voice would be represented by changes in electromagnetism on the tape. That is an analog recording. So analog recording is a technique used for the recording of audio signals. The first systems for audio recording were mechanical, such as the phonograph. So it's really interesting to think about. There wasn't even any electricity involved, right? We were literally cutting a groove into a piece of wax or a piece of vinyl. And that groove was the recording, right? No electricity needed. This could be a hand-cranked system. Later, electronic techniques such as tape recording and microphones were developed. These helped us get better quality through capturing a stronger and more amplified signal that was better at capturing details. So analog recording methods need to be stored on some sort of physical media, right? So record, or later on reel-to-reel tape or cassette. And the signal may be stored as a physical texture or a fluctuation in the field of magnetic recording. And we'll look at that in a little bit more depth as we look at tape recorders. So acoustic recording, right? This is the oldest form of recording. We're cutting a record. And we can see here through a super close microscope, the sort of needle on a record and the groove that is being cut, right? So you can see here these sort of grooves. This is very similar, you know, if we think of in a DAW, if you're familiar with DAW recording or with any program like Audacity, you can see the waveform. So basically the needle's job is to cut a waveform into this physical medium. Here's an even bigger, closer, right? This is a stereo recording, so you could see the waves of the left channel on this side, and over here, because of the video, you can't really see the caption, but it says waves of the right channel. So again, here's the needle in the middle. So here's what early recordings looked like. This is a 1913 recording of a London Symphony Orchestra. Notice the musicians are sort of not in their sort of typical stage format, nice and spread out. They're all kind of cramped next to this tube here that's connected to the phonograph machine. It's interesting, you know, just to kind of see, looks very different than our typical orchestral performance. Let me see if I could go ahead and play that here in our video. So go ahead, maybe write down some words that come to mind when you hear that recording, right? What are the ways you would describe that recording to somebody else? What frequencies does it have? What frequencies does it tend to be missing? So think about that as you're listening to that. Um, So as we move along on our sort of our history of recording, there's a really important invention, which is the transducer, right? Microphones and speakers. So let's look at this technology and see how it really transformed recording. So a transducer is a device that converts energy from one form to another. Microphones, headphones, loudspeakers are all transducers, right? Let's look at a tale of two transducers, a condenser microphone and a speaker. Here we can see the inside of a condenser microphone. Like if you took a microphone and you sort of unscrewed the top of it and looked inside, right? We can see our capsule here, and we can see this very thin plate here. And here we can see a loudspeaker, right? And we could see we have some, just like here, we have some wiring hooked up to some sort of plate. This time it was called a diaphragm. And basically this positive and negative signal, the alternation of that actually pushes the speaker, which then pushes the air in a way that's similar. A microphone works sort of like a speaker in reverse, right? So the air pressure disturbances that it perceives, it then turns into electrical signal that it puts out through the cable into your mixer or into your interface. So it's really important to kind of think about those two technologies as sort of mirror images as one another. Really cool concept. I'm not sure, until I started studying this stuff, I hadn't thought of it that way, but it's a really great way to frame that for your students, right? A microphone and a speaker are just mirror images of one another. They're just doing the same thing in reverse. Ahead here. So let's move on to digital audio. Um, let's think about, well, what is this, right? Digital, right? There's a lot of hype when digital audio first came out. Oh, digital audio is better. It sounds clearer. All these things. Well, let's look at why, or maybe why not. That's the case. So digital audio is a technology used to record, store, manipulate, generate, and reproduce sounds using audio signals that have been encoded. That's the key word here, in digital form. Digital audio signals are comprised of discrete samples that are taken from an analog audio waveform. Instead of a continuous wave, they're comprised of discrete points, right? Think of when you were a kid and you did those coloring books with connect the dots. That's like what digital audio is a bunch of dots that then our psychoacoustics reconnect to represent the amplitude of the waveform approximately. So the next couple slides are going to break down exactly step by step what goes on when you do a digital recording, which you very soon will be doing yourself, or maybe have even started doing, right? So we take the input, which is a sound pressure wave. We have our microphone, which when you sing or play into that diaphragm is moving around, and that backplate is converting that into an electrical signal. So all digital recording is first an analog recording. We still need to use some sort of transducer to convert air pressure into electricity. So all digital recording starts as analog recording. So here's the signal coming into your interface, right? You've got your microphone. Here's my microphone here. I've plugged it into my interface, and it's first thing my interface sees is a wave, right? Then what happens is the sound is sampled, right? You set your sample rate at 41 or 48 kilohertz, and every second it's taking, we can think of them as pictures. They're not really pictures, but they're really just kind of samples. They're numbers, right? If we're using 44100 in 1 second of audio, there are 44,100 samples. That's quite a bit. That's why even though it's discrete points, we perceive it as continuous because it's so quick. The sound is sampled, which is a measurement of the signal amplitude, then taken at a set time known as the sampling rate. So here we can see it's no longer continuous, but a series of points, right? Each of these points has a value that your computer represents in binary code. You can see all these numbers here, right? So your computer is basically creating a log or a ledger of all the different amplitudes at different time, right? That is how we're creating this sort of digital sampling. So there's two really important pieces of technology here, right? There's the ADC, or analog to digital converter, that takes your analog signal, converts it to digital, right? And you record it. Once you record, you're probably going to want to listen to it back. Say, hey, was that a good take? Right? So there's going to be another piece of technology that's either in your computer or your sound card that's called the DAC or the DAC, right? And this is converting the digital signal back to an analog so you can hear it through your headphones and speakers, right? So we're taking this continuous signal, we're converting it to data, and then we have that sort of analog digital signal there that we can then hear. Digital recording hardware. So we've seen some of these devices, right? If you've been in a music classroom that has them, or a friend that has a recording studio, these are all audio interfaces. Why spend money on these, right? Can't we just hook a microphone to our computer and just go? These devices will have really good quality digital to analog converters. Even something like the Focusrite has really nice digital analog converters and analog to digital converters, better than on most consumer computers, right? They also will have different connection types. Like most computers are not going to have, I can't think of any computer actually that would have an XLR, a microphone connection, or even a 1/4 inch, right? Most computers will only have an 1/8 inch cable, so it allows you to hook various common musical cable types up to your computer, and they do a really good job of digital analog conversion. Some interfaces, like you see this one up here, which is the interface we have in our Center for Music Technology, will also be able to sort of help your computer take some of the load of using signal processing. So rather than load down your computer with a bunch of reverb and delay and compression and all those things, it says, hey, let me help you out with some of that. I can actually run some of those plugins natively on my CPU. So there's different sort of levels of hardware, and they each do different things. But essentially, the most important part of any audio interface is the analog to digital converter and the digital to analog converter. So let's talk about two common terms that are really important to share as you're building your personal understanding, really important to share with your students when you're having conversations about audio as well, right? Last lesson, we took a look at hertz and decibels. We're going to look at two other common measurements here when we're talking specifically about digital audio. So these are sample rate and bit depth. When an analog signal is converted to a digital one, two primary factors that determine the quality are the sample rate and bit depth. Sample rate can be thought of how often the signal is recorded in each sound, and bit depth controls the range of possible volumes that can be represented digitally. High bit depth allows for very quiet and loud sounds to be represented without distortion, right? So when we're sampling, we're determining, well, how often are we going to be taking a picture of that sound, right? Again, using that picture analogy. Are we taking, 44,100? Are we taking 48,000? And then bit depth, right? The computer's going to need to assign a value to those. How many possible values are available, right? Is it 16-bit? So there's sort of like those values in that 16-bit scale, or is it 32-bit, right? Which is double, or 24, which is like that sort of sweet spot in between that I will recommend to you to record at. 24-bit gives you everything you need and more without making your file sizes too large. Because that's one thing to think about, right? It's like, well, if I'm recording really big files, I'm going to fill up my computer or my external hard drive really quickly. So you want to find that sweet spot that gives you that high quality without large file size. So let's dig a little bit deeper into sample rate here. So with sample rate, your DAC or your digital audio converter converts the signal to digital. It samples the original signal, taking snapshots at a given rate. The number of times the audio signal sampled per second is called the sample rate, measured in kilohertz or KHZ. Right? Here's some common sample rates. This is what's known as CD standard. Most DAW software, if you don't tell it to do otherwise, will record in this sort of standard. If you're a film score composer or writing anything for picture, it's probably going to be in this 48 kilohertz used for film. If audio is going to DVD or Blu-ray, it's got to be in 48 kilohertz. There are other ones like 96, maybe used in some audiophile or classical music recordings that are very, you want the best possible audio quality. Not so common though. 192, even higher. But again, not super common, not something you'll be doing without really specialized hardware. And anything less than 44.1 is considered low resolution. You probably wouldn't want to do that unless you're purposely trying to get some sort of degraded sound effect, or you want it to sound very digital or distorted. So let's move along. The next thing we'll look at is bit depth. So we can see here, we have this sort of 2-bit signal, right? We can either have, a 0, a 1, or a 2. So a volume is either, if we think about this as musicians, right, we could say this is silence. And this is sort of like, maybe mezzo piano and fortissimo. So we can only have 3 possible dynamics, right? So the music is not going to sound super clear, right? We're not going to have that nuance versus this depth, which we kind of 1, 2, 3, 4, 5, 6, right? So even with the 6-bit depth, we can get a lot closer to representing this nice, looks like the arc in Missouri, right? We can get a lot closer. And if we went up to 16 or 32, we could create those discrete points to very closely represent that sine wave or that arc there. So think about that for a second, right? The more bits you have, the more closely you can recreate a smooth transition. From an audio perspective, the smoother that line is, the less distortion there is, the clearer it sounds. So that's why bit depth is important. 16-bit, again, this is when we're consuming music. This is where we're listening to it. 24-bit depth is common for recording, right? It gives you a little bit more headroom, right? So less likely that you'll clip or cause distortion. 32-bit, also known as floating point, is rare but becoming more common. It's Logic was kind of behind the game on that, and I think in Logic 11 they finally allowed for 32-bit. It's available in Ableton and Pro Tools and things like that. Anything less than 16 is considered a low bit depth. You'll often see what's called a bit crusher, and in different recording software, it's a way to intentionally make your music sound lo-fi. If you wanted it to sound like it's being played on an old NES 8-bit system, or if you wanted it to sound, sort of like a chip tune kind of aesthetic, a video game kind of aesthetic, you can do that where you can lower something to 8 or even 4 bits, and it will give it a very grainy sound. Definitely something that you could demonstrate to your students, or something that you might want to check out yourself as an effect, especially if you're into like video game music or any kind of lo-fi music. Great. Send me an email with any questions that you have about this slide, or definitely reach out to your peers in the peer-to-peer forum. Hope you really enjoyed this presentation. To close out the lecture, I wanted to just make sure that you're comfortable with these terms. So we have sample rate, transducer, bit depth, ADC, and DAC. So take a little time, and in your notes, make sure you write down what each of these things is. Rewind in the lecture if you need to, or refer to other materials. These are all really important ideas in recording. So you want to make sure you're really solid with these ideas before moving on. Thanks for listening to today's lecture. Hope you all have a great day, and look forward to the next one.